First, I'll just introduce Reboot Insiders again for people who might be joining us for the first time. This is just supposed to be simply a forum where people who are really interested in baseball, technology, making players better, math, science, physics, where we can all gather and learn from each other and have awesome discussions. We welcome questions. No question is too crazy, too out there. Any questions you have, throw them in the Q&A. We'll try to get to all of them. We think collaboration is super important here. So that's what this is all about. It's about collaboration between coaches, scientists, players, business people. We just want to make athletes better however we can. So I'll let you guys introduce yourselves. Robin or Travis?
So my name is Travis Ficklin. I am a biomechanist at Dixie State University, which most of you will not realize is actually in Utah with a name like that, and with a name that's probably getting changed here within the next year. But I've been here for about 5 years. I'm lucky enough to get invited to this party because I know Robin. He and I were colleagues and research mates at University of Northern Iowa before we took the jobs we're in now, and that has forever changed the course of my research and thinking life. I was lucky enough to get introduced to Jimmy through Robin, and we now talk to each other weekly and bounce stuff off each other, and to me it's a kick in the pants, so I couldn't be more thrilled to be here. So thanks for having me.
Of course.
I'm Robin Lund. Like Travis said, I'm a reformed professor. I was a reluctant professor, so to speak. I coached college baseball at a young age in my 20s. And then my wife and I started having children, and I pivoted, got a PhD, wound up at the University of Northern Iowa, had an 18-year academic career there. Was lucky enough to have Travis work with me for about 5 or 6 years.
Something like that.
Yep. And my training is actually not in biomechanics. Everything I know about biomechanics, Travis taught me while he was at UNI. And so I'm an amateur, a little out of my depth here, but as somebody who's now applying this stuff on a daily basis, like Travis had just mentioned, I just recently changed jobs. I'm now back in baseball. And so I'm the pitching coach at the University of Iowa.
Yeah, thanks, Robin. No, this is awesome. I'm really excited that I got a chance to meet Travis and Robin. It's awesome in this industry how I think once you're like in the industry, it's a close-knit community and just connections happen and you meet cool people who are really smart and you get to collaborate. So I'm really glad that we got to meet and we can chat about this stuff. I'm sure a lot of people on this call already know who I am, so I'll be really super brief with my introduction. So I'm Jimmy Buffy. My background is in mechanical engineering. Then I got a PhD in biomechanics. And then I worked for the LA Dodgers for close to 5 years, figuring out how to use biomechanics to make players better. And a big part of my job was like collaborating with coaches like Robin and like really learning how to make this stuff actionable, learning what can be used, what can't be used. And it was incredible. And we had a Reboot Insiders talk about a month ago where we talked about different motion capture technologies. And the thing that convinced me to leave my job at the Dodgers and start Reboot Motion was the progress of motion capture technology. It went from 5 years ago where you had to stick all those balls all over your body, and it was a terrible experience, to now you can just capture motion just from an iPhone. And when I was like, oh, wow, motion capture data is gonna be super accessible, that's when I was like, oh, there's an opportunity to start a company helping people make the most out of this motion capture data. Yeah, so I left the Dodgers to start Reboot Motion, and now here we are. I think we're ready to get into some content. So first I'll introduce exactly what I was thinking we could speak about today. And like I said, the last time we did this, we talked about different motion capture technologies as a precursor to where we're going now, which is once we have that motion data, how do we actually analyze it and get something useful out of it? And specifically what I really wanted to focus on today was how we can use physics to make it more actionable. Because in my experience, like where I started with biomechanics, it was a lot of just people applying statistical principles, which are great, but I think adding physics really adds a whole other layer. So that's why we titled this Using Physics to Drive Change, because I think layering physics is inherently a part of biomechanics, but then I think people tend to separate them a little bit. So I think bringing the physics back in can really help us get a lot out of it. But before I really dive in, I was thinking we could try to actually maybe define biomechanics really quickly, because people throw this term around all the time and they say biomechanics, and I feel like it's gotten a certain connotations attached to it. But I was thinking like maybe we could first start by defining it. So I don't know, Travis, you gave a good one earlier today when we chatted. You want to start?
Sure, because when people ask what I do and I tell them I'm a biomechanist, they don't necessarily know what that is. So I will just tell them that I study the physics of human movement. Super oversimplified, but it's really I think it's the nut of the whole thing is those mechanical principles, those Newtonian mechanical principles at the core of it all. And so I think it works. I'm glad you brought physics up because that's kind of my favorite part of this.
Yeah. I'll let Robin back clean up here because I love his explanation from a practical perspective. So I'll just chime in, like the word biomechanics, I think it has the definition literally in the name. It's like principles of mechanics, right? Force equals mass times acceleration, torque equals inertia times angular acceleration. So it's really applying those principles of mechanics to biology. And the biology here is the human body. But that's like a scientific definition. I loved how Robin described it just from a practical perspective earlier.
Yeah, for me, it's like from a coaching perspective, it's describing human motion in an objective way. I give a lot of talks at coaches clinics, and I'll bring up biomechanics and I'll talk about motor learning and those things. And I just tell them that in its simplest way, biomechanics is literally the what. It's just describing what we're seeing in the human movement. That can be qualitative or quantitative too. And I think people forget about that you can do a really robust description of what's happening. And that's essentially a form of evaluation or assessment. And then if you're lucky, you can get in, maybe explain why these things are happening that you're looking at.
Yeah, for sure. And I want to actually like hone in on the word why. We're going to dive into this. But I think like we're going to talk about today, like typical biomechanical analyses, like I said, they're generally focused on like statistical comparisons. And statistical comparisons are awesome at telling if two things are different, but they're not so great at telling why one thing is different than the other. And I think that's a really important part of what we're going to chat about today. But so the first thing I want to do though, before we really dive into some of the nitty gritty, we're talking about physics. And I don't know, Travis, if you want to take a shot at just like generally describing movement, and I have some thoughts here, but I want to like give you a shot since I know this is your thing of movement. Like, how would you describe movement in a physics perspective? What is movement?
Yeah. So Robin brought up qualitative analysis, which is hugely important, right? That's where application is a part of things. Good coaches can watch somebody move. So let's say we wanted to talk about a pitcher. A good coach is going to be able to watch that pitcher and see things very well and know some things that need to change. And the more experience that coach has, the more pitchers that he's seen, the better information he can give. So then if you add a layer to that with maybe some video capture, or you add a layer to that with even slow motion video capture, now you're able to stop things, forward things, back things up. You have more in-depth qualitative analysis. But if you add to that, now you get to maybe measure some things, right? So maybe you rely on like the old school of digitization, which I don't think ever really goes away, to be honest with you. But so now you have measurable things. So to me, and the way I break this down for my students is there's really two ways you're going to look at most things. You're going to look at things from a kinematic perspective, which is you're going to describe the motion that you actually saw so that you can measure things, you can calculate things. Those things might involve positions, velocities, accelerations. Those can be linear things. Those can be angular or rotational things. And then you can connect that information to a kinetic analysis. And so now you're going to start talking about things like forces, and you're going to start talking about things like torques, which are going to influence the motion that's happening linearly and influence the motion that's happening angularly. So once you reach a level where you're measuring more things, now you have a record, or as Robin put it, you have the what. And that's something that somebody like me can do well enough, but then you have to apply that at some point, right? You can go around describing everything you want, but you have to go beyond what to so what. And then as Robin put it, the why. And that's where people like me have to work together with people like Robin to use the information.
Yeah, sure. Definitely. And I want to add like the what, the why. I like to think about movement in a very like generic, general sense, just from a physics standpoint, as a human. Like this applies to walking, this applies to any time you move. As humans, right, we push on the ground and the ground pushes back. And those ground reaction forces add energy and momentum to our bodies. And then when we're talking about cause and effect, it's those forces and that energy and momentum that flows through our body that creates movement. Like energy and momentum are like literal movement. And that's how I think about all movement. And that's how I think like we can really start to get at like Travis was saying, the influence of certain things on other things. But actually, we already got a few questions from the panel, so I don't want to keep them waiting. So I think, so this is a really good point that Art made. We're talking about biomechanics from a very like broad general scope, but we can also talk about the biomechanics at a very small scope. We can talk about the biomechanics of bones, right? Sure. Stress on a bone. How does a bone fracture? We can talk about the biomechanics at an even smaller level. It's literally applying mechanical principles to the human body. But we got a question from somebody, and I wasn't planning on getting to this till a lot later, but I think it's okay to bring it up now. The question is, would you say the hardest part of biomechanics is trying to explain it to people, like trying to explain it to players? And I think, Robin, you're probably the most qualified to answer this one. So would you say that's hard or easy, or how would you describe it?
I guess I would say it doesn't matter. It's critical. Like, it's so important that it doesn't matter if it's hard or easy. And so for me, I've spent a lot of the last year and a half in this new position, drawing on all my experiences as a teacher. So for 18 years as a professor, when Travis left, I actually had to teach biomechanics for about 6 years before I left. And it's taking those concepts and making them digestible. So a couple of thoughts. I don't shy away from big words, and I'll use things like kinetics and kinematics, and I'll talk to those things. I'll say adduction. I'll use those words with my guys, but I just make sure I define them first, and I make sure that they understand them. So our guys are actually pretty slick, or even though none of them are really exercise science majors, they understand a lot more than you would think. So I think it's a challenge, but it's so important that it's one of those things where you can't make a change unless the kid really gets what we're trying to do. And they have to believe you that if you make this change, it's an important change, it's going to help you. But I use a lot of video. I produce little videos for the guys and a lot of comparisons. I find a lot of videos of guys that I think move really well. And I do it that way. Bring in a lot of science, a lot of anatomy, lots of propaganda, and then sell the heck out of it.
Yeah. And I just want to add too, I think I'll speak for myself. I feel a big part of my job is almost like being like a biomechanics translator, right? Like I went to school for a long time, longer than I want to discuss. And Travis did too. And Robin did too. We all went to school for a very long time. But the way I see it is coaches are already talking in biomechanics, right? Saying move faster down the mound, or keep your shoulder closed, or lift your lead arm higher. Like things that you're saying, you are instructing somebody to move their body in a certain way. And that is like literally biomechanics. I think what you can really think about it as, that's like the application of the biomechanics. The coach is like doing almost like an internal biomechanical calculation in their brain. That's, if we keep the shoulder closed longer, it will transfer more energy from the lower half to the upper half, which will then allow you to throw harder. So I think actually, to me, it's not about it being super hard to explain. I actually think it's more about connecting the physics and these like really fancy terms and quantities to things that we're already saying and doing. Like coaches are already doing biomechanics. I don't know, Travis, would you agree with that?
Yeah, totally. I would, and it leads me to a question I would ask Robin, which is, so somebody like me is most likely to interact with somebody like Robin. That's how my normal professional life works. I don't necessarily directly communicate with athletes. I will at times, and they ask questions and I answer questions and so forth. But really, if I can understand what it is that coaches say to athletes, and if I can understand that vernacular and then translate numbers that I measured, or things like, and say, get down the mound faster translates to this variable. It's connected to this variable. And then I trust somebody like a Robin to be able to decide how much of that really needs to be explained to the athlete, which athletes can handle knowing more, which athletes need to know less because they just can't, they're not the type of athlete you'd want thinking too much while they're in the act of performing, and so on and so forth. So there's a couple of layers to that, right? There's really, the number of things you can measure far exceeds the number of things that are worth measuring and worth communicating about, in my estimation. And so maybe I'm the first filter in that whole pipeline of things, but then I think somebody like Robin is the next filter in that. And because of the fact that he knows his athletes, he knows their mental and psychological makeup, he can do some things to decide, how much. But I will say this, because I've known coaches, maybe not in baseball, but other sports and things like that, that basically carry around with them a gigantic lookup table. If they notice a technique flaw,
Yeah.
they have an instant list association with here's the fix for it. And they may not ever understand mechanically why that fixes the thing, but their information is good and it fixes the thing. I think that if I do a good job communicating with coaches, maybe I expand their lookup table, but more importantly, if they come across something that's novel, that's not already in their lookup table, they have just a little bit more ammunition to be able to decide things, try and implement some solution or whatever, or maybe even to have enough savvy and knowledge to know that that's not actually a problem. We're not going to mess with that. We don't need to correct that. And if we do, that we might be coaching athleticism out of somebody.
That's awesome. And I really love the concept of a lookup table. That's a really interesting way of putting it. And we got a few more, man. I got a lot of stuff in the outline, but we're getting a lot of great questions. So I think we should give the people what they want and continue going after the question. All right, we'll take the first one from my guy Stefanos. The interaction of ground force and biomechanics. Has there been any work with force plates and motion capture at the same time to identify cause and effect relationships? Travis is nodding. You want to give this one a shot?
Yeah, for sure. I don't know if this question is specifically aimed at baseball analysis, but the answer is yes, that synchronization does exist. And most motion capture labs that have both three-dimensional motion capture and force plates, those things are synchronized. From a clinical standpoint, that gives a whole, array of things that you can do in terms of understanding lower extremity biomechanics. And so maybe you care about things like injury risk, knee injury risk, or things like that. From a performance standpoint, then you can more directly measure things like impulse, and you can connect that impulse that you're measuring that's being generated from the ground, and you can see that impulse is going to change the momentum of the pitcher's body. So I'm going to go right back to baseball with this. It's going to change the momentum of the pitcher's
Travis,
body.
Can you define impulse real quick?
At its simplest root, impulse is a change in momentum. So from a variable standpoint, that would mean if we look at forces, it'd be some amount of force applied over some duration of time.
So if you're stuck on a force plate, you're going to see the curve go up and go down, and that force over time is the impulse.
Perfect. And let's just take it a layer deeper. When you see that force curve over time, the area under that curve, that's the impulse. So the bigger that area is, the more momentum has been generated in that body. But then if you couple that, because the question talks about synchronizing that with the motion capture, now you can see, all right, where did that momentum go? How much of it's in the lower half of the body? How much of it's in the trunk? How much of it's in different segments of the arm? And that gets me pretty enthusiastic.
Yeah. Robin, have you had any experience with force plates?
I haven't used them very much, just with Travis. We did a little bit with, we had a project going on with some college pitchers where we were throwing weighted vests on them. Do you remember this one, Travis?
Say it again. You're talking about the weighted vest thing?
Yes.
Oh, man.
Pretty great idea, but we were having to jump from force plate to force plate and it freaked them out. So we ended up having to build a ginormous deck of our entire lab to mount the force plate.
Yeah, I believe the ace of our softball staff used, I want to quote this phrase carefully, it makes my knee feel funny.
Yeah, so we're like,
oh, God.
Done.
Yeah, but just to summarize a little bit, I think force plates are so important because, like I talked about, the initiation of the movement of the thing is always pushing on the ground. What's really cool to think about is just like the ground, like the earth is obviously massive relative to a human body. So we push on the ground, it doesn't budge, but it pushes on us and we can budge just because the ground is so much more mass than us. And like understanding the direction that you're applying those forces, that's the thing that starts it all. And so I think, if you have force plates, awesome. And I think this actually dovetails nicely into a question from Art about how many programs use biomechanical analysis tools in college and the pros. I'll answer the pros real quick. It's escalating super quick. I don't know. I would estimate like probably more than half of MLB teams now have motion capture technology and are exploring using biomechanics. And us at Reboot Motion we're working with a few teams ourselves on biomechanics. So it's really, I think, we're approaching like a golden age of biomechanics in baseball. Biomechanics Society was just started by Dr. Glenn Fleissig and ASMI. So I think we're approaching a golden age in baseball for this. Let's see.
Collegiately, I believe there's only one college program with like their own actual motion capture lab. I think that's Wake Forest.
Did I see Georgia Tech tweet something out about?
We've got they're building a new facility. I'm not sure if they'll have motion capture in there. I know quite a few programs will take advantage of labs that are on campus. How much of that is so we can tweet out a picture, a video of a stick figure so people think we use this stuff, and how much actual decisions about guys. But it's not, I don't think at the college level, full blown 3-dimensional motion capture, but just daily and analyzing video, I think is being done at varying levels of efficacy up and down the country, I'm sure.
Yeah, I think it's worth noting that all universities are going to have a biomechanist somewhere on campus. Not all of them necessarily care much about sport performance, let alone baseball. And there's various reasons for that, but a lot of the economic incentives on a campus have to do with grant writing and clinical research, because it draws that kind of money. A lot of times you will find maybe somebody who's a clinical biomechanist, but who actually really loves the sport performance and can do it on the side or do it as hobby projects, but it's not always a natural fit. A lot of places probably wouldn't hire me because I'm not going to write for NIH grants. It's not something that drives me quite like trying to understand run faster, jump higher, throw harder. So I think that's worth noting. We're talking about a lot of this in the context of sport performance, but a huge amount of actual biomechanical work is clinical in nature and really doesn't examine performance.
I would add too that that's a skill in and of itself. So just because you're a biomechanist and you're just like, oh yeah, I'll analyze your kid's swing. That doesn't mean you're going to be any good at it. You may understand some physics and biomechanics, but there's a lot of nuance to this game too. And I know that Jimmy, I'm sure you're much better at it today than you were 8 years ago. And yeah, just going into a lab and having somebody collect one pitch or one swing on you, and then I don't know if that's worth very much.
Yeah. So I think we have a ton of awesome questions, and some of these are super specific. Mike, maybe you guys can answer. I think there's some really specific ones that we can save till later, because I really want to introduce some of the stuff that's in the outline. So I'm going to save some of these really specific questions for a little bit. But Mike Ressler just asked, and maybe Robin and Travis, you can answer this one real quick. Mike asked, given we can measure so much, what areas of research are you both most excited about exploring? And I know we could probably talk about this for hours, but maybe give like a quick 2-sentence so we can like actually get into some of the stuff we wanted to get through in the outline.
So I'm somewhat of a methodology geek, so I get pretty excited about being able to fine-tune methods to do things like better determine real variability separate from error variability, and then I'm also going along with that, I think all the time about limitations of different methods of collecting data, right? So if there's limitations in markered motion capture, there's limitations in markerless motion capture. And so what could those limitations be hiding from us, and how do we try and overcome those? But that said, I'm really interested there's 2 things that get my brain going lately. One is attaching biomechanical measurable things to deception on the part of a pitcher. I kind of got sparked on that based on a study I read some time ago that had to do with kinematic analysis of penalty kicks and what things were most likely to fool a goalie. And I think that's right up there with when a hitter is tipped to pitches, when a hitter is reading a pitcher, what biomechanical tips might there be? And because it's probably much deeper than just arm slot if you think about where your eyes probably pick up first and so on and so forth. So I'm excited about that. And then I'm also excited about biomechanical changes that come with fatigue, right? So not just in pitching delivery, but then actually maybe even at the muscle fiber level. Those types of things get me pretty enthused.
For me, I totally applied now. My research questions are driven by issues I'm dealing with particular players. And I have 3 really hard throwers. I have 3 kids that are pretty, if they had to wind it up, are going to be north of 95, and they're under 2000 RPM spin rate. So they're low spin, high velo guys. And so Mike even knows some of this stuff that we've been messing around with Diamond Kinetics' ball. And we used our Edgertronic cameras, and we were able to actually increase the spin rate on 2 of those guys, like by 300 RPM on 2 of them, but not the other one. And I don't know how we did it. So I want to keep digging. And this is an area that I think a lot of people have maybe given up on, that spin rate is this inherent thing that you can either do or you can't do, be high spin rate go or not. And I guess I'm not ready to give up on that yet. So that's an area that I'm interested in.
No, definitely don't give up. We have a lot of ideas. I think it's just hard because it's a really hard thing to measure. But I think once we get better at measuring it, which we're doing with all of these tools, like the pitch tracker ball that Diamond Kinetics is developing, high-speed cameras, I think as we get better at measuring it, I think we'll be able to get at that question. I think, all right, so here's my plan. We got a ton of awesome questions. So what I want to do is I want to quickly say what the plan was going to be for what we were going to talk about. And then we'll get back to the questions. And that way, if people want us to follow on to the thread that we were planning on talking about, they can follow on that thread with questions, or we can continue going on the questions. So what was in the outline is we wanted to start to get into different approaches to analyzing biomechanics, with the first approach being more of a statistics-based approach, where we just have like comparison groups and use statistics to figure out what's different there. The other thing we wanted to chat about was what's gaining popularity is like an energy flow or energy transfer analysis. And we talked about forces adding energy to the body, where you can literally analyze the flow of energy through the body. And then the last approach we were gonna chat about was a momentum transfer approach, where is instead of analyzing the energy flowing through the body, you analyze the momentum flowing through the body. And I think all of these have pros and cons. That's what we were planning on getting to, but I feel like we got to give the people what they want. I don't know. Would you guys agree? Should we keep going with the questions?
It's all good.
All right. So if people want us to start to go down, like I said, typical biomechanical analyses, energy transfer analyses, momentum transfer analyses, pop those questions in. We'll try to get through the questions first, and then we'll see where we're at. All right. Emilio asked, piggybacking on the lines of impulse and even force plate integration, what is the first step in moving away from a rigid body analysis and actually determining deformation in certain body parts segments under different applied forces? I think Emilio studies this stuff. So it sounds like he's trying to, I'll try to rephrase a little bit. So it sounds like what he's trying to get at is, and Emilio, please put another question if I don't get this right. What is the first step in actually getting a little bit more granular and actually analyzing like how the force actually changes like smaller body parts, like maybe a ligament or like a bone or something like that? How do we go away? How do we move from this really big picture biomechanical analyses into something that's a little bit more granular and maybe literally start to calculate the load on the ulnar collateral ligament or something like that? I don't know if one of you guys wants to take a shot at that. It's a pretty tough question, but I think a really good one.
So I got two things to say about that. One, Jimmy, I think you should take a shot at that, because I know you've done a bunch of that modeling and probably have been a long ways down the road of finite element analysis. But that said, I'll even take it one step further. And this is going to be me totally avoiding answering Emilio's question, because he's got us in a headlock here. So this is me kind of tapping out a little bit, but there's even more to it than that. If you think about, for example, elbow joint loads, right? Joint force and torque at the elbow. We calculate that based upon a whole bunch of assumptions. One of those assumptions is that the pitcher's arm is very similar to all of the, we'll call them inertial parameters. So say, for example, his forearm is very similar to all the forearms from which we derive segmental mass and moment of inertia data. So moment of inertia being how hard is it to rotate the forearm on this axis versus this axis, which we ignore, and so forth. Because a certain amount of that segment is muscular, and because muscle's basically like a sloshing bag of water, when you are executing a pitch, the moment of inertia, I would expect it actually to change a little bit. That's a really disconcerting thought. You have to, at a certain point, you have to accept some limitations to your mathematical model. The current one that we use turns these segments into rigid bodies because it's the most sanity preserving model. But I've seen segments modeled as damped mass spring systems, and it gets really messy really quick. And I think if you really want accurate stuff to even look at that granular level of ulnar collateral ligament, that's the kind of stuff you're going to have to do. I think it's really hard. I think mathematical modeling and simulation is probably going to be an effective way to try and do that kind of stuff, because to measure it in vivo during a pitch using current motion capture technology is really hard. Maybe impossible at this point.
Yeah, I think we can blend, actually. That, I think, segues nicely into two other questions that we got. Art asked about integrated EMG.
I thought we were going to ignore EMG.
Well, to get at, and if we want to start to get at like really understanding what's going on, the muscles, the ligaments, we really have to understand like what the muscles are doing, because there's a bunch of stuff that crosses your elbow, for example, a bunch of muscles, a bunch of ligaments, and because the muscles are redundant, right? You have a bunch pulling this way, a bunch pulling this way. You don't really know how to distribute the forces among all of those things. The only way you can really do that is you stick a wire in the muscles or slap an electrode on it and measure the EMG. I know people have done it. It's not pleasant, but I think, yeah, if we want to start to get more and more granular, I think we need to start to figure out better ways of understanding what the muscles are doing, and also more and more accurate motion capture, which I think Miles asked, could we talk about the trade-offs between basically lab-based high accuracy analyses versus in-game data, but at the possible expense of data quality, which I think you want to do you want to start to get at really granular things. You need more accurate information. But Robin or Travis, you want to chat about that for a second?
I mean, for us, if we're raising money right now, like we want to have our own motion capture lab. And for us, like to me, it's even at the expense of a little bit of accuracy, we would have to go markerless because of just time constraints. And we only have these guys for 20 hours a week, and any data that we collected would be part of those countable athletically related, activities, those CARA hours that we have to put in. And so I would want to get the data collected markerless, and then all of the work would be done on the backside. And I personally would, if there was a trade-off in accuracy, I would be willing to give a little bit up just for the speed of data collection.
Yeah, I think a lot of it this trade-off, I think a lot of it comes down to what you're trying to get out of it. If you are really interested in understanding super granular, the stretch of the ulnar collateral ligament or something like that, you need something that is super accurate that you might not actually be able to apply in a game setting. For Robin's purposes, if he's just trying to figure out, about how high should this person lift their lead arm to generate or to transfer a momentum to their torso, you don't need something super accurate and super granular. That's something that you might even be able to see on video. If Robin is interested in maybe messing with somebody's stride length, right? You don't need something that's really super accurate to really understand stride length. So I think this trade-off versus super accurate lab setting versus game setting, or maybe something that's a little bit easier to capture, is really about what you're trying to get out of it. I think is a big part of that. Travis, did you have anything to add there?
Yeah. Trade-off's the key word. I like the word trade-off because the truth of the matter is there are some issues with markered capture that you avoid by going markerless too. Like you don't have skin movement artifact, for example. And then even the thing that maybe sometimes people don't understand is that even with markered motion capture, you still have to mathematically model joint centers. And that's dependent on a lot of things as well, like marker placement, whether or not those things moved. Like you better hope you don't have a super sweaty pitcher and stuff like that. And anyways, all that said, I think one of the great trade-offs is, you get game data, that's their performance. If you want everything they can give to a pitch, it's going to happen in a game. It's not going to happen in your lab. It's going to probably be close in the lab because it's such a highly repeatable motion, but still, there's no substitute for game-like conditions for really driving the full motion out of somebody. And then the other thing is, not only do you get that, but you get a lot more trials. So you have the opportunity there to have a large number of trials for a given pitcher that goes into his aggregate sample.
Yeah.
And so that kind of stabilizes what you consider to be his delivery.
Yeah.
The extremes of measurement error wash out over time when you do that.
Yeah, and just to piggyback on your point of the game is the pitcher's performance. If you're trying to understand something about injury risk and you use data that you get in a lab, let's look at how hard this person is throwing in a lab. It's funny, sometimes I see these biomechanical analyses of injury risk, and then I look at the person's average velocity and it's 82 miles an hour. And I'm like, let's look at what he throws in the game. Oh, he's 95 miles an hour. Do we think that the forces that he's using when he's throwing 82 miles an hour are the same as the forces he's using when he's throwing 95 miles an hour? So I think you got to be really cognizant of trying to apply lab-based data to what someone is actually doing in a game. Sometimes I know that there are cases where people do throw hard and get to game-like conditions in a lab, but I think you got to be really careful there. And Leslie asked, and I think that this piggybacks off something that we were just chatting about with, again, going back to how do we understand things that are going on in a very granular way. Leslie asked if we need a giant motion MRI machine. It was really cool. I thought about trying to see if I could use one of these, but have you ever seen, I think it's called an XROM, either of you? X-ray of moving morphology?
No.
It's really cool. There's a lab at Brown that I was thinking about collaborating with, where it's literally like a high-speed X-ray machine. So it's for like specifically capturing the motion of a bone over time. It's like literally measuring the bone. The problem is it's a high-speed X-ray machine. So you're exposing somebody to a lot of radiation, a ton of X-rays over, and also these machines, you've seen them, they're massive.
Yeah.
And usually the lens is super small. So if you're trying to get the elbow right, okay, I think the elbow is going to be right there. Okay, did we get it or did we not get it?
That's what you're doing with an Edgertronic for release. But
Yeah.
the stakes are a little higher, and I'll bet time in their lab is really costly because I'm betting that's not a cheap machine.
Yeah.
But as far as the exposure to X-rays, I think we did say there are trade-offs.
Yeah, but to talk about how we can use that stuff though to help us here, I think one thing that we can do is in like a lab-based setting, we can measure things about muscle mechanics. All right, like we can, measure how much force somebody can exert with a bicep. We can measure like the stiffness of something. We can measure, like material properties of the UCL using an ultrasound. And then what's cool, part of my PhD was using a computer model. So now we can measure those properties in a lab setting, put them into a computer model, and then simulate the delivery. So I think like modeling is a really good way we talked about this earlier, but a really good way of using those lab-based measurement tools to apply to start to get at things that are more granular. But it's also always important to remember that that's just a model, right? So it might tell you some things, but you got to be careful about understanding your assumption.
Totally agree, but it also probably tells you more than we can currently do. You can play around with your model, and if you can forwardly dynamically simulate a pitch based on what you think should go into that model, you might be wrong, but you're wrong. There's a high probability that you're in the ballpark, because getting all of those things to be just right to cause the motion that you've been measuring through inverse dynamics, you're barking up a good path there. There's no way to really ever know for sure, because it's all in vivo, right? It's all in a living, breathing human being whose arm is functioning. And so you don't really ever get a look inside that thing during the pitch. It's just really hard unless you have one of these XROMs. But even then, maybe you can't execute a max effort pitch in one of those yet. But maybe that's coming. I don't know.
Yeah, I'm going to see if I can get a picture of one of these XROMs. So my friend, Dr. Matt Chan, asked the question specifically for you, Dr. Ficklin. He said, can Dr. Ficklin talk about the difference between center of mass and center of gravity?
Yeah, I can just give you a mathematical definition of a center of mass. It's the weighted average position of all the body's mass. So if you think of every particle of mass in your body, where is it on average located? And the way we model that is to say, well, the forearm has a center of mass, the upper arm has a center of mass, the trunk has a center of mass, the head has a center of mass. And each of those things account for different proportions of the body's mass. So if the trunk is about 42% of the body's mass, it goes into a weighted average with a factor of 0.42, whereas the head might only get 0.09 or whatever. And then you can pretty accurately locate the center of mass of a human being from video and in motion capture. And I'm trying to think back to DePena and DeLeva's work on this. There's a paper that almost all of us ever cite, the DeLeva paper on. He's the only person I know of that's ever out Jesus DePena, meaning like just getting it so right that Jesus finally said, this is never going to get done, so I'm out. But anyways, long story short, it's accurate to within a couple centimeters for males. It's a little bit more variable for females, and pretty trustworthy. In terms of center of gravity, I treat that as the same point. So
yeah, I mean, I think
I hope I answered that okay. But
yeah, I think it was great. I think in most situations they're the same. There are probably some edge cases. I don't know if we need to get into all the specifics for right here. All right, so there are two more open questions, and one of them is actually related to our agenda. I think, though, the question about Tommy John, I think we may be able to talk about that for a few minutes, and then actually for the last 10 or 20 minutes, however long we want to stay around and people stick around, we can actually get into Leslie's question, which is what we originally had thought we were going to talk about. All right, so have people been able to pinpoint, this is like the $1 million biomechanics question.
For sure.
Have people been able to pinpoint why some players get Tommy John and others don't? And even more so, how much it's happening now as opposed to in the past. And I'm sure everybody on here I don't want to say I'm sure. some people on here might not know what Tommy John refers to. So I'll tee us up real quick for what that is. So we have this ligament in our elbow, like right here, the ulnar collateral ligament, and it basically connects the forearm bone to the humerus. And there's a bunch of other stuff that connects those things here. But when a pitcher pitches and goes into max external shoulder rotation and then inwardly rotates the arm, that ligament experiences stress and then it tears. And Tommy John surgery is essentially just repairing that ligament. So I don't know if people, well, I'll wait to give my thoughts. I'm curious, Robin or Travis, how do you feel about how people answered the Tommy John injury?
I think it's multifactorial, and I think for each guy it's different. I think things like just mechanical efficiency, I think, plays a role in it. How stressful. I know some guys can throw 95 with 70 Newton meters of torque, and other guys will throw the same speed and it'll be in, triple digits. And then I know workload can be an issue with that if guys don't ramp up properly and overload those tissues, and things get really tired and then things aren't firing. And then now the ligament's got to take all the load and it can be injured that way. And I think just like performance in and of itself, like harder throwers, you've seen some of that work, right? Where they compare two groups, one group of pitchers that have had Tommy John and the other group that hasn't, and they compare how hard they throw, and the group that was injured on average throws 2 to 3 mile an hour harder than the other group. So I think there's a lot of things that go into it, and it's multifactorial. And I hope we answered this question, but I'm not holding my breath. I think it's a tricky question.
Yeah, I think theoretically we understand.
Oh, sure. Mechanisms.
The factors, right? It's just such a hard thing to prove in a statistical sense, because even though it feels like there are a ton of Tommy John surgeries, from a statistical standpoint, it's not that big of a sample size. And also, it's really hard to understand all of the other variables. So generally, when we're trying to do some type of statistical analysis, we need one outcome variable. Did this person get Tommy John or not? But at the same time, yes or no over the course of their entire career, or yes or no tomorrow. So first of all, like, the when is a really important piece of that. And then, like Robin was talking about, there are a bunch of other factors that theoretically we believe contribute. One of them, I'm sure, it's just a fact of physics. You apply more force to something, it stretches more, it's more likely to break. So we apply more force to the UCL, it's more likely to break. And theoretically, people talk about that a lot. But then that doesn't account for, like, how strong is your UCL? And is the strength of your UCL different from someone else's? Then we also have a bunch of muscles that cross over here. How strong are your muscles compared to somebody else's? How turned on are your muscles compared to somebody else's? Then also, people don't talk about this very much, but what direction is your arm accelerating in? There's just so many different factors here. And also the amount of time, right? Like Travis was talking about impulse, right? So people often, when they analyze a UCL tear, they just look at the peak force. But if you look at a bunch of research about what causes injury, it's not really peak. It is peak, but it's also the rate of the force being applied. It's the distance of the stretch. So I think, like, theoretically, we can point to 1,000 different factors that contribute to someone needing Tommy John. And I think theoretically, we can be very confident that those things cause Tommy John. But does that mean that we can predict who's going to have it? No, because it's really hard to measure all of those things in somebody.
Yeah, I don't think, I'm glad you said that. And I also don't know. We want to mitigate injury risk, but you got to remember that some of the things that lead to really good performance, like one of my favorite variables is rate of force production. So a very athletic, powerful person not only can generate big forces, but can do it in very short periods of time. And it's dependent upon things like muscle fiber twitch characteristics and so on and so forth, but also activation. I'm glad you said, how turned on are the muscles, because sometimes it's not a question of strength, it's a question of activation.
Yeah, right. Definitely.
But a really high rate of force development is also going to be associated with a high rate of loading on those viscoelastic structures. And it's the rate of loading that's can you
explain viscoelastic structure?
Dang it. I thought I'd slip that one in. Yeah, so viscoelastic just means that the stiffness of the structure is dependent partially on how fast you stretch it. So if you think of silly putty, which if you stretch it really, not saying that UCLs are silly putty, but if you think of silly putty and you pull it slowly, it stretches. But if you pull it really fast, the tension gets so high that it just breaks. And that's a little bit like a viscoelastic structure. When you stretch a UCL really fast, that's more dangerous to it than if you put the same load on it but apply it slowly. And so if you are a pitcher who is capable of high rates of force development, which is going to be all of the guys that Robin coaches, anybody at that level and above is going to be like that. They're also making high rates of loading on those structures. And so you've got those pitchers are going to have to develop tolerance for those loads. Just like any other biological tissue, they can respond favorably to training loads and become stronger. But then there's some things you can't control. Like, what if the cross-sectional area of mine is just smaller than it is for Robin? He and I go out and throw the same pitch, same mechanics, same everything. I rupture mine, he doesn't. Who's that on? Who's to blame for that? I don't think you can. It is so multifactorial and there's just so many things that are slightly outside of control. But that said, a certain amount of Robin's job and all of our jobs is trying to figure out what might mitigate that risk the best that we possibly can. But I don't think you can do it without some risk.
Yeah, it's really interesting. Like, people have tended to focus on two things, I think, because they're the easiest to measure. I think people tend to focus on things that are easy to measure. People tend to focus on easy. I'm going to put easy in quotes, but the peak force and then the amount of pitches you throw in a year, or the amount of innings you throw in a year.
Yep.
And yeah, like we just talked about, if you only try to control those two things, there's 1,000 other things that you're missing. And I think also something that people have talked about is when you focus too much on, and to your point, Travis, about like things adapting and things can grow and change. There's a danger in like limiting pitches and development too much. You limit somebody too much and they don't get a chance to adapt for like newer and greater loads. Like, people tend to, if injuries occur, people tend to pull back, but really maybe you want to inch forward a little bit so you can actually create the adaptation you need. Because we all want starting pitchers to throw 250 innings a year. We want people to, last the whole season. But then we try to get them to do that by having them throw less. I don't know. I think like it's more about modulating the load than limiting it. I don't know. People tend to focus on these things that we're missing, I think, so many other things.
Yeah, you got to build. We're in the middle of that right now. Like, we open up in 2 weeks and it's a grind because mentally guys are over it. They've been thrown to hit. First of all, we built them up in bullpens to a point where they've never thrown that many pitches before without hitters. That's hard for them to get through. Yeah. They got to get through it. But you don't do it all. You don't eat all 76er in one bite. You got to eat them. You got to take lots of little bites. And so we add about 10 to 15 pitches per week. And we tell our guys to hold everything else stable. So we use the Motus sleeve. All of our guys use the sleeve, and we use that to help us keep our workload constant 6 days of the week. And then the 7th day week, when we throw our live set, that's when we add pitches, and we can monitor some of those things like acute chronic ratio and things that we don't have to get into the weeds on that because some people agree with it, but it just provides us with a way to get guys built up relatively safely.
Yeah. So we're approaching an hour, but we still got just about as many attendees as we started with. We got a few more questions. We didn't touch on anything that we were planning on touching on. Are you good to go a few more minutes?
Yeah, absolutely.
All right, cool. So Leslie actually asked a question related to what our agenda was supposed to be, which was, how can you describe the difference between energy transfer versus momentum transfer? Oh, I think that we can chat about this for a few minutes. Travis, do you want to try and kick us off since this is in your wheelhouse?
Yeah, I love this question. Energy and momentum. I think a lot of people out there that when they hear these terms, energy and they hear momentum, I think they interchange them mentally. And that, I'm just basing that on how I hear people speak. They'll talk about how they built up all this momentum and then they transferred energy to that statement is true. They built up momentum and they transferred energy, but I think sometimes people are interchanging them in their mind. And there's important differences. The primary one.
Actually, sorry to interrupt, Travis, but would you mind like taking a quick step back and saying like why we even care about analyzing this transfer?
Yeah, absolutely. We probably all use terminology like kinetic chains and so on and so forth. And you touched on this earlier. The only source of external impulse that you have is the ground. So what your job, if you're a pitcher, I know we just keep talking about pitching. Biomechanics is so much more, but let's talk about pitching. You have a baseball, and if you're going to throw that baseball hard, then what you're going to do is you're going to impart momentum to it. Where is that momentum going to come from? And if you want to look at it as energy, fine, then you're going to impart kinetic energy to that baseball, both rotational and linear. But I'll stick to momentum for this part. So where is that going to come from? Okay, what's it connected to? That's you. So it's going to come from your hand. You can back this all the way up, right? Where did your hand get its momentum? Got it from a forearm. Where to get that? Upper arm. And we can trace it all the way through the trunk, all the way back to the ground. And the only thing that the pitcher is touching that can cause a change in momentum is the ground. And so therefore, the interaction with the ground is going to generate momentum in the body at large. Okay. So if you want to just really super simplify it, you're going to take something that's very massive, which is a human body, and you're going to cause momentum in it. And momentum is mass times velocity. Let's just keep it simple like that for right now. All right. Body has a lot of mass and small velocity. If you could somehow squeeze all of that momentum into a baseball, which has a small mass, to satisfy laws of physics, it's going to have a huge velocity. In a nutshell, that's what a pitcher's doing. The problem is, or not the problem, but the challenge, we'll call it a challenge, is that the body is not rigid. It's multi-segmental, and you generate momentum at the ground, and then you somehow have to transfer that momentum through the lower extremity, through the trunk, out eventually to a pitching arm. And there's links all along the way, and those links are joints. And those are opportunities to lose momentum in that transfer. And so the more efficient you are, the better you are at taking that momentum from your body and squeezing it into the baseball, if you want to think of it that way. So that's a momentum analysis, and it's similar to an energy analysis, right? As you interact with the ground, you will cause energy in the body, energy of movement. And that energy can also be transferred and tracked through segments of the body. So both those analyses have utility in terms of tracking where the oomph that you started with the ground, how you got the oomph into the baseball. And so they're both good that way. The primary difference to me is whether or not one of them has direction. So momentum is what we would call a vector quantity. So it has direction. And energy is what's called a scalar quantity. It doesn't have direction. So I know people rely on both analyses, and I'm going to say that both have a lot of utility. I really prefer the momentum analysis because of directionality.
Yeah. So I'll piggyback on that real quick. I think energy and momentum are very related concepts. Like momentum is mass times velocity. Energy is mass times velocity squared. So they're very similar concepts. But the thing about energy that makes it a little trickier to analyze is energy has many forms. There's chemical energy, there's heat energy, there's gravitational potential energy. So if you're really trying to do a robust analysis of energy flow through the body, you really need to track the energy in all of its different forms all the way through the body, which is a really hard thing to do, given what we were discussing earlier about not really having a good way to measure what muscles are doing. Whereas momentum is really cool, and that there's only one form. It's really like momentum is it's basically like a utilitarian physics concept that we generally use to describe motion in a universal way, which is awesome, which is I think why Travis and I gravitate to it so much.
Gravitate.
Yeah, but analyzing this flow is super important. And I don't know, Robin, do you want to specifically chat about the application of looking at the flow of momentum or looking at the flow of energy?
It's tougher when you're doing it with video. I think that's somewhere down the road in our list of things to talk about, but it's definitely something I think about. And when I'm looking at the way guys move, but it's pretty tough with just an iPad or just an Edgertronic camera to visualize that, which is for me, the goal, why we want to get our own biomechanics lab, because it's quite possible we're missing stuff the way we're doing it.
Yeah, sure. Definitely. Like, I think what's cool is like with momentum, like piggybacking again on what Travis was saying, like you can measure momentum in 3 dimensions, right? You can measure the momentum in like a Ferris wheel dimension. You can measure the momentum in a merry-go-round dimension. One of the things that we do in our analyses is we specifically look at like, in what direction are you transferring momentum with each body part? So just like to give a really practical example, right? Let's say your lead arm is moving very horizontally. So that's the direction you're creating lead arm momentum. But then let's say your arm slot is like super over the top. Those directions don't interact. So this lead arm is not going to do much to help with this over the top arm slot. So really lining them up, generating momentum on a similar plane is a better way to use all the momentum that you generate, which I think dovetails into Emilio's question about how do you determine efficiency for athletes without knowing their capacities and limitations. I'll kick this one off. I think people use the word efficiency often in a very general sense, but I think it almost comes down to semantics. Like, how do you want to define efficiency? I come from a mechanical engineering background, and as part of my mechanical engineering background, I literally would analyze efficiency, which is all the stuff that we're talking about, which is how much momentum went into the system and then how much went out the other side, and in what direction did it transfer out the other side, or how much energy, like energy is a much more common thing to analyze efficiency with, like how much energy went in one side and then how much energy got out the other side. So you can literally do that calculation, energy in versus energy out. But to Emilio's point, how do you determine efficiency for each athlete without knowing their capacities? I think like it's like a 2-layer thing where you can understand like, where is this energy flow or momentum flow being inhibited? But then as we're trying to dig into why is that being inhibited, I think that's where you need a really good like medical assessment or strength assessment to start to get at why that inefficiency might be occurring at that specific point in the flow of energy and momentum. And I don't know, like, Robin, is that a part of your process with your players, is like looking at their capacities and doing assessments?
When we finally, like, so the way we do our biomechanical assessment, we do qualitatively. We break the movement down into about 6 or 7 different chunks, and we make shortened videos, and then we just play those on a loop, and you watch that, just the load, the hip load over and over, and then bang, things start popping out. And once we decide what is the one thing that we're going to work on with a particular guy, that's when we dig into our assessment that we did with our athletic trainer and a physical therapist, and just a full body, looking at all the mobility issues, control issues, imbalances. We look at strength, and we do our force plate stuff and all that kind of stuff. And we'll start digging in there to see if there's anything in any red flags in there that could potentially be linked to this particular movement, deficiency, we'll call it. And then from there, our athletic trainer and myself, we just get our hands on each guy individually and just start going to work and try to see if we can figure it out. At the end of the day, no matter what, you're going to go on a motor learning plan, because you have to move, you have to learn how to move differently. And if a lack of mobility or a lack of whatever balance, or there's some type of imbalance or something is a part of that, then that's extra work on the side that's being addressed while we're trying to get this particular movement to be a little bit more stable in their movement pattern.
Yeah, all totally makes sense. So like getting back to, I think, the broader topic, I think you can analyze efficiency from a very like literal mechanical standpoint, but then efficiency in the sense of, is this athlete getting the most out of their own body? I think that's where the assessments and that comes in. So you almost have 2 layers here.
Efficiency gets used on with the arm a lot, and I use it this way too, just because it's how coaches talk. I'm not appropriate, but like an efficient arm path. Okay, so what that would mean is I got 2 guys that throw 90. Mm-hmm. One guy is really high stress and another guy is really low stress. I don't know if efficiency is the right way to do it, but that's how efficiency is used in the baseball world with coaches. So one is, that's an inefficient arm path if it's high stress with relatively low velocity. I'm not sure.
Totally makes sense. Yeah.
I think that's a really cool practical definition. If you can stick numbers on it, it's like Jimmy said, there's literally mathematical formulas for calculating it, but what good does that do anybody if you don't have some way to operationalize it?
Yeah, and actually, this is a little bit of going back to momentum and energy, but something that I just thought of that I wanted to mention, because I think it's really important, because we skipped over the typical biomechanical analysis approach, and we went straight to our bread and butter, which is energy and momentum analysis. One thing I want to point out about energy and momentum, in both equations, you have M, which is mass. And I think that is such an important thing to include in this analysis. A typical biomechanical analysis will look at angular velocities, right? The angular velocity of the pelvis, the angular velocity of the shoulders. But what's really missing is like, how big are each of those things? The arm, like, and Travis, you were touching on this, but I guess I'm just like bringing it back to this. The hand can move faster just because it's smaller than the torso. So if we want to analyze what is the athlete actually doing from the torso to the hand, it helps to have them on the same scale, which means you essentially scale them by how big they are. Harold asks, I think this is a great question. Let me see if I can summarize. Coming from someone who had endured Tommy John, I know there are things on the market that measure torque on the UCL. How do we know all torque is created equal? I think we touched on this, but I think we can answer this very specifically. I think he's asking is, all torque on the UCL created equal? Like 75 Newton meters of torque measured by Modis is for one pitcher, is that the same as 75 Newton meters of torque on another pitcher measured in a lab? Is that the same when their form is potentially in a different position? I think he specifically asked, can the UCL handle different loads with the form in different positions? So basically, is all UCL torque created equal? I think is a good way to summarize it.
It's a good question. I know people, I've talked to a lot of pitchers, there's quite a few pitchers out there that have had Tommy John. And I asked that question. I'll ask them, was it what were you throwing? And it's usually a fastball or curveball. Those are the two that I don't hear change ups, but I wonder when you're pronated versus this, that changes the length of that flexor pronator mass.
Yeah.
And is it going to be with the muscle mechanics? And if it's a little bit shorter, a little bit longer, its ability that's a great question. I'm sure it's got to be a part of the problem for sure.
Yeah. I think like people tend to say torque on the UCL. But
Yeah.
what we're really saying is like torque around the elbow. We really have no idea what is experienced by the UCL. And really it's a matter of exactly what we were getting at is how are those forces distributed among all of the structures of the elbow. And like you were saying, like the posture of the forearm, like you can even feel it, changes the lengths of those muscles and changes your capacity to turn those muscles on and use those muscles. And people don't even think about it, but the UCL actually changes length, like with the position of your elbow. So the position of your elbow and the position of your forearm can determine can change a bunch of things about how force is distributed in your elbow. So to answer Harold's question, no, all UCL torque is not created equal. And I will also add that this kind of gets back to what we were talking about the last Reboot Insiders seminar, right? Okay, someone gives you this measurement of torque, but that's all it is, a measurement. What they're not telling you is like, how did they get that measurement? So typically you're measuring the position of something over time, right? And then you have to do a bunch of fancy math to get the acceleration of that thing. And when you do all that fancy math, you introduce a lot of noise, and then you have to apply filtering. And sometimes people choose different filter parameters. Sometimes their measurement devices are different. So that's another thing where 75 Newton meters of torque measured by Modis might not be the same as 75 Newton meters of torque measured in a lab, because they're completely different measurement devices, and people get those numbers in completely different ways. And unfortunately, getting at those numbers requires a lot of assumptions. So that's why I make it a really important point in the analyses we do is I try to not compare numbers across motion capture systems, just because each measurement system has a bunch of its own assumptions.
And nobody loves the Modis Sleeve more than I. Like I love them and we use them every day. But I also think I don't think it was designed to be a tool that was to collect data like in a cross-sectional manner in a day to answer a question, because that thing can, if it's a little bit loose, I've had the guys put them on upside down and it's, oh, you're a submarine guy now because the data is all upside down. And if it moves even a little bit, you just got to be careful. I don't ever think that the Modis Sleeve was ever designed as a research grade.
Right.
But what it is great at, it's like counting calories, right? I mean, over weeks and weeks and weeks and looking at patterns and plotting different things, I think is a wonderful tool. I love it.
Okay, so there are a few more questions. And I think we'll go to Leslie's first because it's related to what we were just talking about. So Leslie asked, does anyone know if there is a specific point in the arm circle that correlates to the moment where the UCL fails? That's a tough one. What do you think, Ron? When you talk to these pitchers who may have actually experienced it, can they pinpoint like where it happened?
They usually can. They think it's right about when they were just going big effort. But I know, like I did my Achilles tendon when I was in my late 20s, and same thing. I just remember pushing off and going to run. I don't remember if it was when I was in the stretching, when the ankle was pushing down and I was stretching it, or if it was during the concentric portion of that move. I just remember a big boing, and so that I've asked guys and I haven't had anybody be able to tell me to pinpoint it, just only when it was high effort.
Yeah. Well, and I think because failing, I think that could mean like different things. Like I don't think for everyone it's like a catastrophic rupture where it just explodes. I think a lot of times you just see like it fray over time, soreness builds up over time, and all of a sudden, my elbow's been hurting, let's get an MRI. Oh, there's a tear. So yeah, I think that's a tough one, but it's a really good question.
I know Harold put in the chat that he said his came when he was coming out of max external rotation.
Yeah, I think that's probably somewhat common given that's probably about the point where that peak force occurs, or maybe it's more to the point of where the peak rate of loading occurs. Travis's earlier point.
Yeah.
But yeah, it's probably common.
And it's not just peak, it's not just rate of loading, it's
Yeah.
also what position is everything in when those things are happening. Because at maximum external shoulder rotation, the elbow is also very flexed.
Mhm.
And that's a lot more exposure to that ulnar collateral ligament also. So all that comes into play. It's really tough. It's really tough.
Yeah. All right. So this question is it's a little bit of a new topic, but I think it's a really good question because I know people talk about it a lot. And I think, Robin, you probably have some good insight here, but do we believe in high stress innings or pitches, maybe the workload for those being different than like an easy carefree inning? And what do you think?
I think if you believe that stress is stress, and I'll give you an example. We have a kid in our program right now where I could just tell something was off with him just looking at him. You start to know these kids like they're like your own children. You spend so much time with them, and then you touch base with the strength coach. Hey, how was force plate data? Oh boy, interesting. He was a little bit down today. He's an Omega Wave user, right? Yeah. What's going on? Yeah, not looking great. And then you grab the kid and you ask him what's going on, and it's my aunt, who I'm extremely close with, is diagnosed with cancer and is not doing well. So you start digging in there, and it's stress. So I guess to your point, it's coming into a bases loaded situation with nobody out, with their best hitter up, and you're coming out and you're breathing smoke out of your nose and you're throwing as hard as you can, is going to be different than coming in a clean inning in a blowout game against a team in a game that doesn't matter. So I believe that if we talk about just stress on the arm, no, it's probably the same, but just like the overall stress of the situation, absolutely, it has an accumulation over the course of the season. I believe that.
Yeah, and I'll add, I think what may be a really important factor here when thinking about a high stress inning might also be fatigue, right? Like I think there's a lot of different versions of fatigue when you get into the like physiology of all of it. But like we have this like super high powered system that fatigues really quickly, right? So maybe when you come into a really intense game situation and you're super amped and all your muscles are turned on, maybe you blow out all your energy really fast and then you fatigue really quickly. And then maybe those pitches are actually like, sometimes I think about it, if our muscles are at full capacity, maybe they're at full capacity to protect the ulnar collateral ligament. But if we blow out all of our energy and our muscles are fatigued, then as you get later in the inning, maybe you're actually like more of the load is being experienced by the UCL. So I think a big part of what someone might consider a high stress inning is actually fatigue. Or is this maybe the pitcher is in his 8th inning of work and all of a sudden the bases are loaded and now he's already fatigued and now you're putting him in a high stress situation where he's trying to amp up that velocity. So now he's even increasing the force that his elbow is trying to experience while he's in a fatigued state. So I think there is some credence to the whole high stress inning thing. A lot of times when people ask me about measuring workload, I think that you can try to get more and more granular. Like probably the ideal thing would be to be able to literally quantify the amount of fatigue and scale like your workload number by how fatigued somebody is. But I think applying a little bit more weight to a situation where you think a guy might be fatigued, I think it's not a bad way of like actually not counting every single inning exactly the same.
Yeah, and Mike Son's work with the fatigue units that has been blended into the Modus app and all that stuff, I think is a big part of that. That's right.
Yeah, we still got everybody on the chat, and we got one more question. So I think maybe this can be the last question. And I think it's a great question because I love how you framed it, Robin, and I think Art really enjoyed it too. When you were talking about like making a change with an athlete, you called it a motor learning program.
Yeah.
And maybe you can just like give a little bit more context for what you meant there.
The history between that was coaching my daughter when I was still a professor. My daughter's a little softball player, and trying to help her run faster and doing a ton of research and basically, hey, you need to do this. You need to do this a little bit better. You talk about biomechanics as the what and the why. What biomechanics never tells us is how do we get there, like the roadmap to actually get somebody to change. And so I started really getting into the motor learning literature because I avoided those classes like the plague when I was a doctoral student. I never took one motor development or one motor learning class all through my master's degree and PhD. And so I was really second guessing that. But anyway, to answer Art's question, I call them motor learning programs where basically it's just a really targeted approach to help guys change the way they move, and lots of variability, lots of different drills. We switch things out, different cueing strategies, internal cueing, external cueing, implicit, all. There'd be another whole, we could do another whole 2-hour talk on
Well,
that stuff.
yeah, that's exactly what I was going to say is we can do all of the biomechanical measuring in the world, but unless like the athlete can apply the stuff that we're trying to do, it doesn't matter. And there are awesome resources for like how people learn, and especially learning like complex movements versus simple movements. And I do think it's really awesome that you think about that stuff, Robin, because I don't think it's a skill set that a lot of coaches have. And but it's so important to really understand how people learn stuff.
I think the most important thing for me is like when we're working on these things, it's is to not jump ship. Like we've all, and I did this as a young coach too. You get a kid and you're like, hey, we're going to make this change. And then you're 8 days into it, or maybe even 2 days in, or maybe even 30 minutes into it. And you're like, that didn't work. Let's try this now. And then pretty soon you get into this at about 8 different strategies later. And this kid's movement is like a Frankenstein monster of all the different things that you've thrown at him from a cueing standpoint. And everybody's frustrated. Like you think the kid's uncoachable and the kid thinks you're clueless, and you're both wrong. And what ends up, for me anyway, for guys to make a real change, I've heard the guys at Florida Baseball Ranch talk about 21 days. And in my experience, it's more 2 to 3 months, and you'll really start to see things stabilize, right? Like when they're in a game and things matter and it's like, hey, he's doing what he worked on. To me, it takes months. And so you got to be really patient with it.
That's awesome.
Yeah, that's awesome. And I think that's a great point to end on, because I was actually thinking that would be another great Reboot Insiders, is actually like trying to apply this stuff. Well, yeah, we'll put this one in the back pocket, but I think this was, holy crap, this was awesome. Amazing questions. Yeah, we got to our outline a little bit. I really wanted to dig in on, which we didn't cover at all, was the typical biomechanical approach and all like the pros and cons with that. Maybe that deserves its own Reboot Insiders. I don't know. We'll see. I feel like you got to give the people what they want, though. I think that's always important. So yeah, I think we can wrap it up there. Robin and Travis, appreciate everybody's time. Panelists, this was awesome. Thank you for all the incredible questions. And I don't know, any closing words, closing comments?
Just that this was awesome. I really appreciate the invitation to talk about this. I agree. Those questions were outstanding. Really fun stuff to talk about. I love admitting in front of a bunch of really smart people that I don't know stuff. So there's a lot of stuff here I just didn't know, and that's really good for me. So I appreciate it. And I hope we will do it again. I hope we'll talk about some of those other things you just mentioned, because I think it's worth digging into some further way.
Yeah, no, thank you so much for asking me. I really appreciate it. It was a lot of fun.
Yeah, this is so much fun. I just want to reiterate the collaboration aspect of this is like one of my favorite things. And I think is probably the most important part of it, because I can sit in my room here and think all that I want and be stuck in my own brain. But until you start to verbalize stuff and have people ask questions, you don't really learn. And interacting with people, there's just a lot of smart people in this world. And if you don't take advantage of it, you're an idiot. So appreciate all you guys. Thank you everybody for watching.